Okay, so I'll be taking about medical image processing. In the last few sessions, I think you have undergone through medical image processing, and also in the yesterday's session, one of the sessions we have studied about filtering the images, non-linear filtering of images. So obviously, I will not discuss about filtering. Rather, I'll be discussing about images, image processing, its medical applications, and then I will show you what work we have done in last few years in this area. So this will be the aim of this presentation. Assuming that few of you may not have undergone through this topic, that is digital image processing. So I am covering some fundamentals also. Those who might, because a lot of teachers are also there, so those who are teaching this subject or those who are aware of these concepts, please bear with me. So basically, okay, just a minute. Okay. Okay. So basically, when we say medical imaging or medical image processing, then medical image processing is actually a digital image processing problem. Only the image comes from the medical domain, or the image is acquired from medical imaging modalities. Okay, so every medical image is a digital image. Every medical image is actually a digital image when it is stored in the computer or when it is stored in any system. If I want to manipulate that image, if I want to improve its quality, it should be in digital form only. Then only I'll be able to manipulate it, or I'll be able to improve its quality. Okay, so basically, every medical image problem is actually a digital image problem. That's why whenever medical image processing is taught, initially the concepts of digital image processing are taught, because they are only applicable, they are only used in medical image processing. Okay, so let us first see what is image, so that you will be clear with the concepts which I am going to teach in the later slides. So image is nothing but it is a 2D function fxy. An image is nothing but it is a 2D function fxy, which means that, so when we draw a signal, say simple sine t, and this is xt, which is equal to sine t. So xt is equal to sine t. So here t is the independent variable and x is the dependent variable. X is dependent on t. So the amplitude on y-axis is dependent on the value at t-axis. This type of signals are called one-dimensional signals. They are called one-dimensional signals. Okay, because why it is called one-dimensional? Because only one parameter is changing. That is, only one parameter is dependent parameter. Okay, and one is independent parameter. So this type of signals, like for example, if this is 0, if this is 1, just for assumption I am taking, if this sample is 2, if this is 1, again 0, again it is -1, -2. So if I represent it in discrete form, then I can easily write it as xn is equal to 0, 1, 2, 1, 0, -1, -2, and so on, depending upon how many samples you are taking and what is the gap between the samples. That is decided by sampling theorem, which we will not be discussing here. Okay. So from this you can easily see that a signal is a one-dimensional data. It can be simply represented using either a single row or a single column. Unlike that, image is a 2D function, or it is sometimes more than 2D, means it is 3D also. Okay, so it is a 2D function fxy. Here we simply write in 1D fx, we write fx or ft. But here we write fxy, where xy indicates, so actually image is represented in form of matrix 2 3 4, like this, not like a signal in 1D. Okay, so every value is called pixel. Every value is called pixel, and every pixel has some location. So 2 will have some location 1 comma 1, 3 will have some location 1 comma 2, then 1 comma 3, and so on. Okay, so this xy is actually this coordinate, which are called spatial coordinates. in signals they are called time. It is called time value, time coordinate. But in images it is called spatial coordinates. Okay, why spatial? Because this is related to space. Space means its location or its position. It has some location in the whole space. So xy represents the coordinates, and the value at fxy is called pixel value. It is also called intensity or gray value of the image. Okay, so what I want you to understand from this slide is that you should just imagine that every image is actually a matrix. Every image is actually a matrix, and therefore when you manipulate an image, when you do some operation on the image, then this this should be kept in mind that it is a matrix. And so if I'm multiplying, if I'm whatever operation I'm doing on the image, it will be a that operation will be performed on actually a matrix. So if I want to increase the image, I want to make the image more brighten, so I'll increase the pixel values by multiplying all the pixel values with 2 or 3. If I want to darken the image, I will decrease its value. So I hope you understand this gray level or intensity, which I am calling it as pixel value. If gray level is high, it means that it is a bright, it indicates brighter portion. If it is low, it indicates darker portion. Okay, so this is how the image is represented. F00, F01, and so on. If the size of the image is m into n, then the matrix will look like this. This is a matrix. Okay, and this is what is called as a digital image. I'm taking this in very brief, not in much detail. So, what are the different steps in any image processing problem? Not only medical image processing, or obviously in medical image processing also, but the different steps in any image processing problem include: first is problem domain. Problem domains means that includes formulation of the problem, data collection, and all those points. Okay, so these 2 points are related to what? Data collection. So you collect data through CT, MRI. In case of medical imaging, we use different medical imaging modalities and we acquire the data. But suppose we are taking a general photo by our camera, phone camera, or lens camera. So it is something like this. This is the object जिसका image लेना है. This is my camera system or the system which will be taking the image. We need some kind of illumination energy like light. If I want to take a picture in with my mobile, then usually we take it in morning, in the daytime, because proper uniform light will be there. In dark, the image quality will not be good. Okay, so light energy is required. So in medical imaging modalities, X-rays or magnetic field or ultrasound waves, they are used as energy. They are used as energy, and here in general scenario, light comes from sun. The energy comes from sun. Okay, so the image is taken by the camera, and then it is stored in our computer system, where it is sampled and quantized. This process is called sample, and this process is called quantized. Finally, it is encoded and it is stored in digital form. It is stored in digital form. Okay, so these are some of the steps which are used. So all of you might be knowing what is sampling and quantization. Okay, I will not discuss that. So these are the steps to convert any analog data into digital data. 3 steps are there: sampling, quantization, and encoding. Okay, so that's why when the image is taken and stored in the computer, it is automatically sampled and quantized and encoded to be stored in digital form. Once the image is acquired, now I want to do image enhancement. Image enhancement basically means improving the quality of the image. Okay, but both image enhancement as well as image restoration, they both improve the quality. But what is the difference between them? In image enhancement, we simply enhance the quality of the image. Now, enhance means simply increasing or decreasing the brightness of the image. Okay, so if I have a matrix with low value, it, like for example, If this image is represented in form of matrix, most of the pixels will be having lower value. Why? Because this image is darker in overall, darker in nature. So what I can do, I can either make them all of them brighter by increasing their value by multiplication or something. So I will make it a brighter image. Okay, so making the image brighter or darker. Sometimes even it happens that some images are very bright, so we cannot see the objects clearly. So brightening or darkening the image is called image enhancement. Okay, and for that different methods are, lot of methods are there. In image restoration, what happens? It is also the technique to improve the quality of the image. It is also the technique to improve the quality of the image. But in image restoration, the noise characteristics is well defined. It is known. The noise model is known in prior. In enhancement, we don't know the what kind of noise is there, or what actually needs to be improved. Exact thing is not there. In an image enhancement, we do hit and trial. We increase the brightness or decrease the brightness, and okay, and then we conclude, okay, after increasing the brightness 2 times, I find that this is better. So it is, so this is subjective. Image enhancement is a subjective process. After enhancing, someone may say, no, no, old one was good. This is subjective. It differs from person to person. And I'm enhancing it maybe 3 by 3 or 4 types method. Someone will say, no, this method has given good result. Someone will say, no, this method has given good result. But image restoration is objective based. Here the objective is fixed. Why? Because noise is known. If noise is known, if the characteristics of the noise is known, then a well-defined mathematical framework can be designed to eliminate that kind of noise or to restore the image. Okay, so it is an objective process, but both enhancement and restoration results in a improved image quality. Hardik, if the if there is some net problem or the net automatically gets logged out, please call me. Okay.
So no problem.
So okay. So the next, in the next step, there is morphological processing. So as the figure itself, you can see that morphology is generally related to, it is generally related to analysis of shapes or minute structures in the image. Like for example, in fingerprint. Okay, so as you can see that this is a fingerprint, its quality is very poor. There are so much breaks in the line. Okay, in between the curves there is so much of breaks. Okay, so we can make it uniform with the help of some morphological image processing algorithms. Okay, segmentation is a process of dividing or segmenting different objects in the image. Different object, because one image may have multiple objects and I am interested only in analyzing one particular object. So I want to segment that. Like for example, in this image, there are two objects in this image. One is the shadow. This is the shadow, and this is the actual my image. This type of figure is called histogram. Those who are teaching image processing might be very clear with this, that this is called histogram. So from histogram we can clearly see, okay, this is one object and this is another object. Okay, and by separating them, if I eliminate this portion through some method, the shadow can be removed. So I have segmented my object of interest. In medical imaging, this is very useful. I want to segment a tumor. I want to segment the lung area. I want to segment the chest area. So a lot of applications are there in segmentation in medical imaging. I want to segment calcification. Okay. Then I have object recognition and object description. So these two I'll cover simultaneously. It is nothing but pattern recognition, which we are discussing a lot of times in this HTTP. Pattern recognition means we have image, the image is now converted into some form of features, some form of variables. Maybe we have segmented the tumor, and now after segmenting, I am calculating its area, perimeter, different features I am calculating from that segmented tumor. Okay, that is called what? Object recognition or description. We are describing the image not as an image, but as a group of features. We are describing the image not as an image, but as a group of features. Like you see this figure. In this figure, there are three features. So one feature lies in this area, other feature lies in upper area, and other feature lies in this area. So I'll not discuss this figure in detail because I want to cover many things today. So I have limited time, but I hope you understood that in object recognition and description, what we do, we extract features from different groups of images, say cancer and non-cancer, and then I plot and see that okay, whether the features are able to differentiate both the groups or not. Like for example, the area of the tumor in cancerous image is larger, and the area of tumor in non-cancerous image may be very small. So the larger will come in this range, and the smaller will come in this range. So we'll be able to differentiate that if they come like that. Sometimes there may be overlapping also. So overlapping in case they may be merged like this. This is for lower, and यहीं पे फिर कुछ दूसरा भी आएगा higher. Merge. So then we'll have to use some other technique to solve this issue. And then these two fields are there, which I'll not give much stress here. Image compression, which is used to reduce the size of the image in order to reduce the computational complexity, or sometimes in telemedicine applications where the images are to be transferred from one place to another. So for low bandwidth requirement, because the bandwidth to reduce the bandwidth because of the low availability of low bandwidth, we need to compress the image. Okay, and then color image processing also includes all these steps, but only the image is in form of color. But when image is in form of color, it is not 2D, it is more than 2D. Okay, like I told you that this is a gray image. I'll not go back. This when the image is represented in form of matrix, it is a simple. When the image is represented in form of single matrix, it is called grayscale image or binary image. But in case of color image, the image is represented by three matrices. One matrix for red value, second matrix for green value, and third matrix for blue value. So what happens in grayscale and binary image is that every pixel will have only one value. But in case of color image, every pixel has three values: red component, green component, blue component. So that's why there are three matrices. So I'll be discussing the application of digital image processing in breast cancer. So you all have at least got some idea, whether those who are new to this field, I have at least got some flavor of what is image processing. And now a few things about this breast cancer and this area has already been discussed yesterday while we were studying nonlinear filtering of images. But today I'll be mainly discussing about classification part, because we are the name of the STT, we are focusing on intelligent computing. Okay, so I'll be concentrating more on computing part or intelligent classification and computing part. Okay, so I'll be very fastly just going through the breast cancer and why it is important. So obviously breast cancer is an important is of great concern, because it is the second leading cause of death of women due to cancer. Okay, and it accounts for more than 1.6% of the deaths overall. In India, 1 in 28 women develop breast cancer during her lifetime. Okay, and it is lesser in rural, it is more in rural areas. 1 in 22, sorry. It is 1 in 22, 1 in every 22 women in rural areas. Okay, so that's why it is of important concern. We know that it is of important concern, and early detection is the only solution. So what is the practice in Western countries is that there a lot of awareness has been created in the women population that they should go for breast cancer screening after every 2 years after the age of 40. Okay, generally they recommend that after 40 years, every 2 years or one after every 1 year, the woman should go for breast cancer screening. Okay, so that early signs of cancer can be detected. So when we say screening is nothing but it is imaging. And there are two common methods of imaging: mammography and ultrasound. Ultrasound is the first choice. If not available, Sorry. Just give me a second. So mammography is the first choice and ultrasound is the second choice, but both have their own advantages and disadvantages. Sometimes ultrasound is also recommended by the doctors because of several advantages which we'll discuss in the coming slides. What is mammography? It is an X-ray of breast. I think you all might have gone to these concepts in the previous session. It is a screening tool and it uses low dose X-ray energies. So the process is like this, that the breast is completely pressed and made as flat as possible, and then X-ray is taken. X-ray beams are radiated and the image is recorded. Okay, so from this only we can understand that it is a painful procedure and it includes radiation, which is also harmful, and it is costly also, and sometimes it is not available at local places, local hospitals, or its availability also now it is available, but still it is less available than ultrasound. Ultrasound is very easily available everywhere. Okay, so that are the drawbacks. But what is the advantage? Why mammogram is the first choice? Because the advantage is that it can show the signs of cancer at very early stage. So see, these are calcifications, small calcium depositions in the breast. So this can be detected with the help of mammogram. And then these can be further quantified by using image processing techniques, that how much is the spread, what is the size of calcium depositions. So all these things can be analyzed with the help of image processing techniques, like I have shown in this figure. It is done by some authors. Okay, they were exactly able to determine what are the exact size of the depositions. Higher size, they were able to separate the higher sized calcium depositions with help of some image processing techniques. Okay, so limitations I have already discussed. The main limitation was what? Painful, harmful because of radiation, and also it has been observed that mammography is not much successful in dense breast tissue. So dense breast tissue means the breast of younger patients. Because in younger patients the breast is very dense, and therefore it has been observed that mammography is not much successful in dense breast, and that's why they are recommended usually after 40, after 40, age of 40. Okay, so we just understood that okay, mammography is the first choice, but there are some limitations, and therefore the second choice is what? Second choice is ultrasound. Sound has lot of advantages, like for example, it is easily available, it is low cost, it is radiation less, it includes sound waves. It does not uses X-ray radiations, it uses sound waves for recording. So these are the advantages. Okay, it is completely painless and non-invasive process, no radiation. But then ultrasound also has some drawbacks. What are the drawbacks? The images are very noisy, as you can see. They look very noisy because of the presence of inherent noise called speckle noise. If speckle noise is the noise which you see here, you see dots, lot of dots in the image in this. That is speckle noise. And then there is also shadowing. There is also shadowing. As you can see, that is an inherent artifact in ultrasound machine, that wherever there will be tumor, sometimes due to this artifact, we see a shadow like this. This is because of the this generally happens in malignant tumors. Malignant means cancerous tumors. Okay, and further there are some more problems also, that whenever radiologists interpret ultrasound or mammogram, they take a lot of time, they have a lot of burden because they have to see so many patients. Okay, so these problems are already there. There are chances of errors also. You'll go to one doctor, it may have a different opinion, other doctor may have a different opinion. Staging is another concern, stage 1, 2, 3, 4. So a lot of issues are there. So that's why, okay, so these are the treatment techniques which we just discussed. The first most preferred choice, mammography for screening and biopsy for confirmation. Biopsy is surgical procedure in which a small tissue from the breast is taken and it is analyzed in the lab, which is called histopathology. So then it is finally confirmed that whether it is cancer or not. Sometimes mammography followed by ultrasound followed by biopsy. Okay, sometimes ultrasound followed by biopsy. This is the second choice. And then others are MRI. MRI is generally used for staging of breast cancer. And then the new technology that has come is breast elastography, which is used to exactly analyze the exact shape, the exact volume of the tumor. So breast elastography is useful in exactly determine the volume of the tumor. Okay, so these things we have discussed. I think I'll skip what is the current pathological procedure is biopsy only. Okay, and to overcome all the problems which we discussed in the previous slides, something which is able to address all these problems is computer aided diagnosis. What is computer aided diagnosis? Do you remember the pipeline of intelligent computing which I discussed? Data, pre-processing, feature extraction, feature selection. Do you remember that? Can you recall that? Are you all there?
Yes, sir.
Other participants are there.
Yes, sir. Yes, sir.
Okay, so do you remember this pipeline? This is the pipeline now.
Yes, sir. Yes, sir.
Data pre-processing, feature extraction, feature normalization, feature selection, and then classification. So this is nothing but it was the CAD only. That was actually computer aided diagnosis. It involves intelligent computing. Okay, so it is said that CAD systems can address the problems of traditional methods. Traditional methods, what were the problem in traditional methods? So already we have seen that images are very noisy, lot of burden on the doctors. Okay, and sometimes biopsy are to be repeated multiple times, because if in one step the result is not obtained, so multiple steps are done sometimes, so biopsy also has to be repeated sometime. Error in reading, inter reader and intra reader. Inter and intra means error within the radiologist, means when a radiologist analyzes the images, then when the radiologist analyzes the images, just a minute, now I'm getting some noise. Deepika, do you want to ask something? Deepika has raised hand. Is there any question? So inter reader variability and intra reader variability means that if a doctor say has to read 100 images in one day, then his suggestion for those images may vary. And say we have a particular image X. So when he reads this image X with 100 images, and then when he reads it in a single, maybe in a very in a day on which he or she has very less burden, so his opinion may differ. His if he take more time, if he takes more time for the same image, his or her opinion may differ. That is called in error within itself. Okay, and then there is something called as error between two observers. Radiologist one gives slightly different opinion, radiologist two gives slightly different opinion. Okay, so these are some errors, and for that we have CAD systems. But remember that a CAD system, again and again I'm telling you, that whatever research has been done till now, they cannot replace doctors, they can assist, they can only reduce their burden. They can help them in making the work more faster, in a more accurate way. And this is the block diagram of CAD system. This is a detailed block diagram that lot of things are required. Okay, so image pre-processing is required, feature extraction, and now statistical significance analysis is also required. For that we have to do normality test. So I'll not discuss this table in very detail. Okay, these are general steps only. For statistical significance analysis we do t test, Mann-Whitney U test. Okay, then we do feature extraction. For feature extraction, feature extraction we have done. So now we do feature selection. Identification of reliable biomarkers is nothing but feature selection. So for that, lot of methods are named here. All these are methods for that. Then we do training. We already studied this. We do training. We can use different classifiers: logistic regression, KNN, random forest, okay, naive bayes, discriminant, and then we develop the model. And this side is testing the model. This is the developed model, and now we are testing it with some new by giving some new samples. Okay, so this is the overall paradigm or overall CAD system. Okay, so this I'll skip because CAD systems also have a lot of drawbacks, so that's why there still lot of new techniques are coming. Okay, and in images, lot of noises are there, so lot of methods are there to remove those noises. For example, median filter, adaptive. So lot of filters are there. Yesterday only we have studied so many filters, like not so many non-linear filters. Okay, so after denoising, once we have image, we have denoised it, the noise is eliminated. The next is what we have: feature extraction. So a lot of features can be extracted from the image. Now from what is the inspiration of feature extraction? So the inspiration comes from this. So now I am shifting to sonography. Okay, because in the yesterday's class mammography was concerned, I am now shifting to sonography. I'm now whatever I am uh, teaching, whatever we are discussing now, it is with reference to sonogram, ultrasound. So in ultrasound, what happens? If you see the next, okay, this from this slide you can understand. This is very important. See, in this particular figure, it is explained that what are the differences between the benign and malignant, cancerous and non-cancerous tissues in appearance, in terms of appearance. So, for example, this is round shaped tumor. The tumor can be round shaped like this or oval shaped like this. One is round and one is oval. One is round and one is oval. Okay. The third is ill-defined shape. The shape is not clear. So when the shape is ill-defined, it is more likely to be malignant cancer. If the shape is not, if the shape is oval or round, it is more likely to be benign. Similarly, limits means the boundary limits. This is called precise boundary limits. Precise means I can easily trace what is the boundary. This is partially precise. Again, at least I can see the boundary. And this is completely imprecise boundary. So again, if the precision decreases, this is more precise, less precise, even less precise. So if the precision decreases, there are more likely the chances of cancer will increase. Okay, so similarly, lot of image features are there. By this, I want to just explain you that image features are there. And now, if I want to extract features, what I will do? I will extract features related to shape, because I just saw that shape is important. Okay, margin is important. Also, if you see another concept, I think it is there. Yes, see this one, eco texture. Eco texture means inside the tumor, what kind of, how the pixels are arranged. Are they completely uniform? Uniform means they are similar. So if they are similar, it is called homogeneous. Similar doesn't means equal. Even if it is nearby, it's okay. But heterogeneous means they have mixed kind of, the texture is not uniform inside the tumor. The texture is not uniform. Somewhere it will be dark, somewhere it will be bright. Such type of texture is called heterogeneous. So from this concept, we have understood that okay, two types of features are very important. One is the shape, that is boundary features, and the second one is texture. Okay, and on the basis of this only, in one of the study which we did, we extracted so many features related to shape and texture. You can find these features there, they are available in literature. Okay, so these features, and other than this also lot of features are there. Other than this also, lot of features are there. Just a minute, I'll give you one example. So, like for example, so I've already told you that image is nothing but it is a matrix. Image is nothing but it is a matrix. And matrix means it includes lot of numbers, lot of values called gray values or pixels or whatever. Okay, so lot of features can be extracted. For example, first order features. So it includes what? Variance, mean, variance, and how we calculate these features. So let me give you one example and then we'll move forward. Okay, so like for example, I have an image, say 1 2 2 3 3 2 5 6 6. Okay, this is my image I. Obviously the image will not be so small, the image size will be actually very large. It will be very large. Okay, so now we find what is the probability of occurrence of a particular pixel. Just to illustrate the concept, we have taken such small matrix. Actually, it is a very large matrix. So what will be P1? How many pixels are there? 9. So P1 is 1 by 9. It has occurred only once. P2 is 2 by 9. P3 is again 2 by 9. P2 is 3 by 9 because it occurs 3 times. Okay. P4 is 0. P5 is 1 by 9. P6 is 2 by 9 and so on. So in this way we calculate all the values of P and then see you can extract these features. What is the formula here? Mean is equal to summation of, so I will little bit expand it. Mean is equal to summation of I is equal to, it is I equal to 0 to, so in our example it was how much? 0 to 5. In our example it was 0 to 6. So the formula will become I is equal to 0 to 6 IPI. So just put the value of I and PI in this. So first value is 0, so nothing to write. 0 into 0, anything will be 0. Then we have 1, I equal to 1 into P1 plus 2 into P2 plus 3 into P3, and then we'll put the value of P1, P2, P3 from here, and then I'll get mean. I'll get the feature mean. And similarly, we can calculate all these features because all these features involve PI. Okay, so in this way we can calculate the features from the image. Another very popular feature which is used still in many papers is gray level co-occurrence matrix. The features that are based on gray level co-occurrence matrix. Whenever you use these features, it is very important for you to understand that how those features are coming. Okay, MATLAB functions are there, Python functions are there, some things are readily available, but still you should try to understand that what is its significance and how they are actually calculated. Okay, so I'll try to explain in brief GLCM and then we will move forward. Okay, so see how GLCM is calculated. I'll not tell the theoretical thing, I'll only tell you, try to explain you with the help of example. So this is one equation. I hope you all can see. I equal to 102 112 021. So in GLCM, gray level co-occurrence matrix, in it is called GLCM feature because in this first you have to calculate a matrix which is called as co-occurrence matrix. Co-occurrence matrix. So what is co-occurrence matrix? This is my image matrix. This is my image matrix. After getting the image matrix, after getting the image matrix, uh, after having the image matrix, we need to first find the co-occurrence matrix. How to find this co-occurrence matrix? See, co-occurrence matrix is nothing but number of times. Here n is indicating number of times. This n is indicating number of times. This n is indicating number of times, 0, 0 is coming together. Number of times 0, 1 is coming together. Number of times 0 and 2 is coming together. I hope you are getting. Number of times 2 and 0 is coming together. Now, what do you mean by coming together? Okay, so that we will see now. So, to determine that how many times they are coming together, we define two parameters first, d and theta. See these two parameters. D is the distance, which is usually taken to be 1, and theta is angle, which will be either 0, 360, it means this direction, 90 degree, this direction, and then one will be in this and this direction. There can be 4 possible directions. The different angles are there. Okay, see here. Please see carefully now. So we had this matrix. And now from this matrix, I am calculating F10. F10. 1 is the distance. Sorry, f d theta. Yeah, 1 is the distance and 0 is the angle. So 0 angle means I have to remain horizontal this way. And d equal to 1 means I have to check only 2 adjacent pixels. Only 2 adjacent pixels. So what does that mean? See, what I want to calculate first, n00. N00 means how many times 0, 0 are coming together. So in this matrix, can you tell me how many times 0, 0 is coming together in this matrix? Any one of you? In this direction, how many times 0, 0 is coming together? Any one of you?
Three times.
Okay, so Deepak said 1. What about others? Okay, Deepak is saying 1. What about others? 0. Dr. Rima is saying 0. Okay, so Dr. Rima is correct, 0, because 0, 0 is not coming anywhere. See where it is coming. 0, 0 at the distance of 1 is not coming together. Okay, let us take another example. How many times? So that's why the first value here is 0. Now let us find n01. Now I hope you will understand. N01. See, in this matrix, I have to find n01. If I go in this direction, I'll not get any 01. This is 1 0 0 2 1 1 1 2 0 2 2 1. Distance 1 means I have to take only 2 pixels at a time. Means adjacent pixel. Now let us take in this direction. So 0 1 I am getting 1 time. 2 0 1 1 2 1 2 0 1 2. So I am getting only 1 time. That's why this value is 1. Coming to the next, N02. N02. I have to find N02. How many times now can you all tell me? In the same direction. 0 degree. 0 degree means right and left, horizontal. How many times? You can message also. Okay, I'm getting 2 answers. A lot of people are telling 2. Okay. So let us see. 02. So 102 is available here and 102 is available here. I will not take 20. I need 02 only. In whatever direction I move, I want 0 first and then 2. So 2 times it is coming. That's why, see, this value is 2. Let us take last one more. Let us now find N21 and then I will move here from here. N21. N21. How many times? 1. Few people are saying 1. So 2 1. So 2 1 I can find when I go in this direction. I will find 2 1. This pair. When I go in this direction, again I will find 2 1. So I am getting it 2 times. See, it is 2. And this is for 0 degree. 0 degree means horizontal, this side and this side. Similarly, you can find for 90 degree. In case of 90 degree, we have to show up and down. I hope you will do now. Okay. 45 means you will see this side and this side. Okay. And 135 means you will see this side and this side. So in this way you will get 4 co-occurrence matrix, and from this 4 co-occurrence matrix I will calculate so many features. See, Fij is the co-occurrence matrix. I'll put co-occurrence matrix in this table, in this formula, and I'll get lot of features. So you can read the original paper by Harlick. This is proposed by Harlick's features. They are called Harlick's features. So you can find this explanation in detail. Okay. So after getting Fi, we can find lot of features, and we'll get 4 values of features. Okay. So we can average them. In lot of research papers, they have averaged them for all the angles. After calculating for individual angles, sometimes they use it separately. Sometimes they find average of it. So after calculating the co-occurrence matrix, you can find ASMs, contrast, correlation. For all that, we have equations. We can simply put in that equations and we can calculate these features. So we have so many image features, as you can see in this table, and lot of other features are also there. I have not included everything. Once you get features, we have to do feature normalization. We have to do feature. This also I have discussed in the pipeline of intelligent computing, and now you can easily understand that. See, so many different types of features are there. First order statistics, Harlick's texture feature. uh, all these features will give different range of numbers. Some features may give only numbers between features value between 0 to 1. Some may be very high, some may be very low, some will be in between. So the dynamic range of features are different. So that's why this feature normalization is important. Otherwise, what will happen when you apply so many features to the classifier together, the classifier may be biased towards the features with higher value and may neglect the features with lower value. That's why feature normalization is done. And feature normalization is nothing but bringing all the features in a same range. A lot of techniques are there for feature normalization. This is a simple technique called as linear scaling to unit range. Means the range between 0 to 1. This is the formula. The new value of feature is equal to its old value. Like for example, the range of feature is coming out to be the minimum value is 2 and the maximum value is 10. Okay, so this minimum x is 2. The maximum xi is 10. Minimum xi is 2. And then there will be so many values. Means after 2 we'll get, say suppose for some images we are getting 3, for some images we are getting 5, for some we are getting 2.1. So this xi is the individual value. These 3 will be fixed, minimum and maximum will be fixed, but the value of individual xi will change, and in this way it will be converted. If you easily put it, you will see that all the values will come, because will come in the range of 0 to 1. Okay, just a minute. Now after this, after feature selection, in some of our study, so I have discussed filter method. Okay, in my previous session I discussed that there are 2 types of feature selection method. One is filter method, in which we rank each feature, which one is first, which one is second, and for ranking we use some criterias: mutual information, gain ratio, symmetrical uncertainty, chi-square. These are some criterias. And in wrapper method, we try to find the best subset of features. Okay. We don't try to rank the features, individual features. We try to find the best subset of features. So some well-known algorithms are sequential search algorithms like forward, backward, floating forward selection, recursive feature. And obviously, a lot of optimization techniques are now used for feature selection, genetic algorithms, and a lot of algorithms are there which are used. In one of our studies, we did multi-criteria feature selection. In multi-criteria feature selection, what we did was we simply combined all the feature selection. Like for example, I gave you one example in the previous class, right? That if I select the best student in the class, so a lot of criteria can be there to select. One is the CPI, percentage marks. Other can be what? Who is performing best in sports. So there may be a possibility that someone is best in sports, but his class rank is 3 in with respect to percentage. So overall, he should be better or she should be better because he's, and there may be a possibility that someone is getting first rank in class, but he's very poor in sports. But if I take only CPI, if I take only CPI, then I'll select that person. So taking only one criteria may not be sufficient to select the best feature. So multi-criteria feature selection can be done. So what was done? The features were passed through many different feature selection techniques, and finally majority voting was conducted. Here, finally majority voting was conducted. I hope you all know what is majority voting. Like for example, if information gain, IG means information gain. If IG says that F1, F2 is best, then F1, then F3. GR says F1 is best, then F2, then F3. Chi2 says F1 best, then F2, then F3, then F2. So now by observing together all these three, I find that F1 is best. This is called as majority voting. Okay, IG voted F1 at second, GR voted F1 at first, Chi2 voted F1 at first. So F1 is getting more votes compared to others. So F1 will be best among these three. This is called majority voting or multi-criteria feature selection. So in this way, we can develop our own feature selection techniques also. Okay. And now finally comes machine learning. So I have discussed the fundamentals in the last class. After feature selection, we need to do what? Classification. So in the last class, I discussed artificial neural network, right? Is it correct? We were able to complete one problem, right?
Yes, sir.
Okay. So now we will be seeing one of the other very popular classification problem. Very popular machine learning problem, which is called support vector machine, which is invented by V.N. Vapnik and Alexei A. Kervoranikis. Okay, in 1963. So what is the key idea behind support vector machine? It is kind of supervised learning classification. First of all, in the last class we studied supervised and unsupervised and semi-supervised, which is also called reinforcement. So this supervised machine learning classifier is a supervised classifier, first of all. And what is the key idea? The key idea here is that given the features, like I told you, suppose I want to classify 100 images of benign tumor and 100 images with malignant tumor. So I will extract some features. And when I plot those features like this, suppose this is area and this is perimeter. Two features I have plotted like this. Just for example, I am taking, okay, area and perimeters. So the aim is, no, sorry, it is area only. It is one feature only. I have plotted area like this corresponding to two classes. Red is one class, say it is malignant, and the other unfilled bubble is, say let it be, I am writing it as black. Black is another class. Say one is malignant, other is benign. And I have, so this is area and this is not area, this will be only benign and malignant. Red is area, one is malignant, other is benign. Okay, so the aim of support vector machine is to, the aim is to find a optimal separating hyperplane. What is hyperplane? You have, the aim of support vector machine is to find a boundary first of all that can separate the two classes, and then this boundary is maximized with the by hyperplanes. I'll just show you. See, so many boundaries can be there, right? So this is one, this is another boundary, and there can be multiple boundaries. That can be easily seen that there will be many boundaries. So this is one boundary, this has, there can be multiple boundaries, as you can see. So which is the best? Which boundary is the best? Okay, so now a new boundary is selected such that, yeah, just a minute. Okay, this is the complete figure. See, now a new boundary is selected such that the boundary should be in as center as possible, first of all, as center as possible, like the black line in between, and from that back line, black center line, we make two more lines, the dotted lines, this one and, so this one and this one. Okay, such that there are some features which lie on the second line. I hope you're getting or not. Just a minute. Okay, just a minute. Okay, this is the figure. So the center line will be this, and then I will make two more lines. One line passing through this feature, and one more line passing through this feature, this one. And the aim is to maximize this region. The aim is to maximize this region. Why this line number 1 and line number 2, and this is C, center? While line number 1 and 2 are passed through the features, they're passed through the, one is passed through this feature and one is passed through this feature. The points lying on this bond, this 1 and 2 boundary is, are called support vectors. They are called support vectors. So the line is passed through support vectors, and the main, and the aim is that, and the aim is that the gap between the two classes, this is one class, okay, this is another class. So the aim is that this line which is crossing through the this in this area, and this line which is crossing through these areas, this gap should be maximum. This gap should be maximum. This is the purpose of support vector machine. This is the purpose of support vector machine. See this figure, I think you can understand very clearly. This center line is Wx plus B equal to 0. It is exactly located at center. Okay, and then these two are the support vectors, this one and this one from one class, and this is the support vector from other class, and the data is separated like this. The data is, just a minute, the data is, I hope you're getting. So what is the aim here? That I have these two lines, okay, the boundary is at the center, so I have these two lines, so I have to maximize this gap, but I cannot take it more, I cannot cross the features. So the features lying at the boundary of these two lines, they are called as support vectors. They are called as support vectors. Okay, and the main boundary is in the center itself, but it is assumed that this, the higher will be this margin, the higher will be this margin, the better will be the classification. Okay, so that is the main aim here. In this is I'm just telling you what is the aim, and how it is done, that also we will see. Okay, so SVM is a supervised classification technique, so it also will work in the same manner. We'll first train the model, so training is done, testing is done, Data division is done, tenfold, fivefold, hold out. All these we have studied in the previous sessions, and we get some classification after training. When you will do testing, you will get classification output that whether it is benign or whether it is malignant, and then we do performance evaluation like accuracy, sensitivity, and all those things. So how actually this support vector machine works, now see in this example. In this example, you can easily see that there are two classes. One is shown by blue and other is shown by red. Blue and red. Blue is the negative class and red is the positive class. You can see by this figure. Okay. And we are taking 3 points. 3 points are there. S2, S1, S2 and S3. They are shown by the arrows. They will be the support vectors. It's quite easy to say from this figure, right? So this is one class, this is another class. So the center will lie here somewhere, here, and this two will be support vectors, and here this will be the support vector. So this will be the total hyperplane. I hope you have understood. So three support vectors are there, S1, S2 and S3. The first aim is to find these support vectors. So we got S1, S2, S3 by this figure. You can easily find it. I hope you all have, you can easily get these values. S1 is how much? 1 in the y-axis, and I think it is how much? 6, 5, 4, 3, 2, 1. 2 in the x-axis. Here you see. Here you can easily see S1, the value of S1, S2 and S3. You can easily calculate it from the graph. I hope. So you can calculate it, right? What is the value of S3? S3? The y value is 1 and the x value is, the y value is, where does S3 lies? 4. This is the top and this is the bottom value in the matrix. Okay, so for S3 the lower value is 4 and upper value is 0, this point only, because it is exactly lying on the x-axis. Okay, so we can just assume that the values here are written as s equal to yx, and this is y and this is x. Okay, so from this figure you can easily find this S1, S2, S3. Okay, now how this support vector machine is applied. So first of all, we apply some bias b equal to 1, that is simply added in each S1, S2 and S3. Why this bias is added? Because now we want to find the center. We want to find the center. Support vectors we got, and now we want to find the center. Okay, to find the center is not always at origin. The center does not always passes through this 0. Wherever it is 0, the center does not passes through 0. So the center may be shifted from 0. So we start it with 1, assuming it to be 1. So that's why we add one bias in all these three, the same bias in all the three support vectors, S1, S2 and S3. Okay, after that we do some mathematical calculations, which I'll not go into very detail, but definitely will get an idea. We calculate Lagrange multiplier alpha 1, alpha 2 and alpha 3. Now what are they? They should satisfy these three equations. If you see these three equations, they are very simple. See, in the first equation it is simply alpha. In the first equation it is alpha 1 S1, all has to be multiplied by S1. So this is S1 into S1, this is S2 into S1, this is S3 into S1. Alpha 1, alpha 2, alpha 3. Then S1 into S2, S2 into S2, S3 into S2, S1 into S3, S2 into S3, S3 into S3. So this is multiplied by S1, then S2, then S. All the combinations are formed. The first one is multiplied, and each had a coefficient of alpha 1, alpha 2, alpha 3. Okay, and the first one was negative class. First two were of negative class. S1, S2 are of negative, and S3 is of positive class. Is this equation clear to everyone? Please tell me if is this equation clear to all of you. Some of you have to reply whether this is clear to all of you. I'm waiting for some replies. Otherwise, I'll have to repeat. Okay. So it is clear to Deepak and Dr. Vairam. Okay. So now, once you do this, so in this way, we first form these equations and we find three constants alpha 1, alpha 2, alpha 3. So we do some matrix manipulations, calculations, and we get these three equations. We have done nothing, but we have simply substituted the values of S1, S2, S3, which we wrote in the previous slide. After putting, we'll get these, we'll do multiplication and we'll get these three equations, and then I'll get alpha 1, alpha 2, alpha 3. Alpha 1, alpha 2, alpha 3. Finally, we got this after solving these three equations. Finally, the formula for hyperplane is this formula. W is equal to alpha I into xi, which means that it is simply summation of alpha 1 into S1 plus alpha 2 into S2 plus alpha 3 into S3. So we have substituted all the values alpha 1 S1, alpha 2 S2, alpha 3 S3. And finally we got this as the final answer, final hyperplane. And now if you plot this, see it is what? 1 0. Weight is 0, bias is 3, and the boundary is 1 0. So 1 0 means, see this green line. This green line. Bias is 3 means that it is shifted to 3 from origin. It is shifted to 3 from origin. Okay, means we have to find a line combining these points. And then we have 1 0. So definitely one point will be 0. It is shifted to 3. It is shifted to 3. This is 0, 1, 2, 3, 4, 5, 6, and so on. So it is shifted by 3, and one point is 0. Okay, and other point can be 1. So we can make one point here and we can join all the points. We can join all the points to get this hyperplane. So in this way, the hyperplane is formed in the support vector machine classifiers. But the problem just we took was linear problem, straight line. But most of the problems are non-linear, as I told you earlier also. So for that so such type of problems are called non-linearly separable problems. Non-linearly separable problems. Okay. So like for example, see this one, I cannot make a straight line. This one, this here also, if I make straight line, these two are left. Some portions are misclassified. To solve such non-linear problems, there is a concept of kernel. There is a concept. So kernel is nothing but what we do after extracting the features. If they merge with each other like this, like blue and red, you see the features are merging with each other for both the classes. So we have to now transform them into a, we have to now, just a minute, I'm taking a call, it's urgent, I think. Okay, so I was telling you that this is another problem, that the previous concept which we studied, only linear problems can be solved, and most of the problems are linear. So we use kernels before classification. What kernels will do is they will transform these features. So like just imagine, all of you just imagine, just see these red bubbles and see these blue bubbles and just stretch it up and down. All the red bubbles should be stretched up and all the blue bubbles should be stretched down. So when the blue bubbles come down, red bubbles go up, there we can find some line in between later on. So this stretching of the features are done using this kernels. Kernels do what? They transforms the feature into higher dimensional space. In technical, it is called higher dimensional space. Their features are same, but they are scaled such that they go in certainly different space. Okay, like earlier, if some features are earlier here, they will go somewhere else, maybe here. Okay, this is, and that is done using different formulas. Different formulas are there. I will not discuss that. Even y equal to x square can be also a formula. These are nothing but polynomial. This is polynomial 1 plus x square. This is nothing but 1 plus x square to the power, maybe more power can be there, 2, 3, whatever. Okay, this is simply x square. Xt into xj means it is x square only. So we use some formulae to transform the features into different space, and then we can get the, like, see, this is very difficult to classify. Okay, so I am skipping this problem. I will give you slide, you can do it. Okay, the same process is applied. See, here also it is difficult because 4 features are here internal, so I have to make a circle. I cannot make a straight line, but if I want to make a straight line, I can first use kernels. So here these kernels are used, this kernel function is used, and all the features were transformed to some new value. They were having some old value, they are transformed into some new value. Okay, and after getting a new value, now when they are plotted, see, now easily a straight line can be formed. This is because of the kernel. So with the help of kernels, we can solve non-linear problems also in SVM. Okay, so with this, I will now take some applications. Okay, so there is one example of unsupervised learning also. This will take 2-3 minutes. This is simple. Okay, I have directly taken a question. Cluster. I hope you all remember what is unsupervised learning. In unsupervised learning, the label is not available. Whether it is benign or malignant, that is not available. Only data is available. Features are available. So suppose we have 5 features here. A1, A2, A3, A4, A5, A6, A7. We have 8 points in the XY axis. I want to get it categorized into 3 clusters. These 2 clusters, 3 clusters, 4 clusters, that is decided empirically by experiments. Okay, there is no in brain. Suppose I have a brain data, and if I want to know how many tissues will be there, it will be very difficult to decide. So generally people take 5 or 6 in complicated images. Okay, so we have how many points? 8 points, and the question is saying that we have to divide it into 3 clusters. And which technique is to be used? K-means clustering. And in K-means clustering, it is a popular technique. In K-means clustering, we have to use one distance formula. So the distance formula which we have to use is Manhattan distance formula. Don't worry about these complicated names. Okay, they are just there's just some equations. It is very easy. We'll just come to know it. So what we do in this kind of clustering problems is, when we have so many points, 8 points. Okay, so what I have to do, I have to group them into 3 clusters. First cluster will have some points, second cluster will have some points, third cluster will have some points. But when you will do this clustering, we need some criteria to do this clustering. So what are the steps that are followed? In step 1, we simply select 3 cluster centers. What are cluster centers? If I have 3 groups, say this is one group, this is one group, and this is one group, 3 clusters. So many points are there in this group, so many points are there in this group. So there will be one cluster at the center. At the center, or you can say one cluster will be representative of all samples. There will be some similarity between this center cluster and this center point and all other points. Okay, so because k is equal to 3, we have to, please mute your mic. Because there are 3 clusters, we will take three cluster centers. So what cluster centers we assume? 2, 10. A1 is taken as one cluster, A4 is taken as one cluster, C2, and A7 is taken as third cluster, C3. So out of the given 8 points, 3 points are randomly chosen as clusters C1, C2, C3. See, so the first cluster was 210, the second cluster was 5, 8, the third cluster is 1, 2. And after that, we find the distance of these clusters from all the points. We find the distance of these cluster centers from all the points. So we'll have to now find distance of cluster center 210 with point 210. Obviously, it will be 0 because all the points are same. Well, it is the same point. The distance between 210 and 25, 210 and 84, 210 and 58, like that. And how do we find the distance? We need some distance formula. So formula which I am using here is this one: x2 minus x1 plus y2 minus y1. Simple formula. This is called Manhattan distance formula. So if I want to find distance between 210 and 25, this one and the second point 25. Okay, so how I will find the difference? X2 minus x1 simply means 2 minus 2 mod plus 10 minus 5 mod. So answer will be 5. So I'll get 5. Similarly, we have to find the distance of each cluster center with all the points. Like for example, when I will find the distance of cluster 3, cluster center 3, 1, 2, तो 1, 2 का जब आप 1, 2 के साथ करेंगे तो 0 आएगा, और 1, 2 का जब आप 6, 4 के साथ, if you calculate the distance 1, 2, 6, 4, how much will get? 1 minus 6 mod plus 2 minus 4 mod. How much I'll get? 5 plus 2, 7. I got 7. Okay. I now got the cluster distance. Now from that, what we do finally? This is the last step. Okay. So after this, we'll end this techniques. I'll just discuss some of my published papers. So see here. Now you just see which value is lowest. So in the first row, this value is lowest. So it means that this point belongs to C1. It's obvious. For second case, which value is lowest? This value is lowest. So the second point belongs to C3 cluster. A3 point belongs to C2 cluster. A4 point belongs to C2 cluster. So I have written C2. A5 belongs to C2. A6 belongs to C2. A7 belongs to C3. A8 belongs to C2. The minimum value, according to the minimum value, the minimum distance, because it's obviously that if a distance between the cluster center and the data point is small, it means they are in the same group. They are in the same group. So now the clusters have changed. Earlier, you have got 3 clusters. Cluster 1 में क्या आया? केवल in cluster 1 we got only this first point 2, 0. In cluster 2 you got many points 2, 2, 2, 2. Last one also. So it means that we got 5 points. So all points are there. In cluster 3 we got 2 points. Now what we do, again we calculate the average. For cluster 1, no need to calculate the average. Average will be 210 itself. But for cluster 2 and 3, we can calculate the average. See, I have calculated the average of both x value and y value. And the calculated average is the new cluster center. The calculated average is the new cluster center. Now again repeat this process. Again find the distance between these cluster centers, new cluster centers, and all the data points. And this process is continued until center of the newly formed clusters do not change. When the cluster centers stops changing, then only this process stops. Or the data points remain present in the same cluster. The data points are not changing their clusters. And finally, the number of iterations are reached. In an algorithm, I will say only 100 times this algorithm should run. So if that is reached, then also the process stops. This is example of unsupervised learning in which we get different clusters by using some criteria. And these are so many applications of this intelligent computing in which I am working. Okay, this is only on the basis of, and obviously I'll work on many more applications, but presently I've worked on breast cancer classification, lung sound classification. At present, one of my student is working on bimodal classification of breast cancer. We are working on mental illness like schizophrenia, Parkinson's disease, epilepsy, neurodevelopmental disorders like dyslexia, and language disorders. And we have done some work on CT images also for COVID-19 detection. Okay, so these are some of the works which we are doing. And I'll just, because the topic was for breast cancer imaging, I'll just discuss 2 3 papers in 2 minutes, and then we'll be having the question answer session, means discussion session. Okay, so this is one of our paper. Okay, so in this paper we used fuzzy cluster based neural network classifier for classifying breast. Okay, it is opening in the PDF. Okay, anyway, so okay, so fuzzy cluster based neural network classifier for classifying breast tumors. In this, we developed a new technique by combining both supervised and unsupervised learning. This is the name of technique: fuzzy cluster based neural network classifier. So we used fuzzy Siemens clustering also, and we used neural network classifier also for classifying breast tumors in ultrasound images. Okay, this is 2016 paper. So what we did in this paper, I'll just explain you in brief, so that you can have similar type of. So this is what we did. I don't know whether it is visible or not. Okay, so see the same steps we used. This is your the first. So I'm not able to use my pen. Okay, so try to see this my this cursor. So this is our image, breast ultrasound image. We do pre-processing, we do noise removal. Okay, then we extract features, we normalized features, we do feature selection. After feature selection, we splitted the data into training and testing. That is clear from this figure. We are splitting the data into training and testing. Okay, after splitting it into training and testing, so when we use in the training data was first passed through unsupervised learning module. Unsupervised learning module, FCM. See here, I have highlighted FCM. Why we passed it through FCM? Because our data was real-time data. When you collect real-time data, lot of outliers, lot of noises are there in terms of sample values and number of samples. So we first passed it through fuzzy Siemens clustering, and we assumed 2 clusters. Like in the previous problem, we solved using 3 clusters. We assumed only 2 clusters. So we got 2 clusters, cluster 0 and cluster 1. We analyzed manually both, not manually, we wrote some program. So the both the clusters were analyzed. If in a particular clusters, if some cluster has more malignant samples, we call it as malignant cluster. If some cluster has more benign samples, we call it as benign sample. And in benign cluster, if we find 2 or 3 malignant samples, we remove it from the training data set. Similarly, from the malignant group, if we find some 2 3 samples of benign, we remove it from the training data set. In this way, we try to improve the quality of the training data. And then we use neural network for classification. Simple. Neural network for classification. Okay, see this, from this it will be very clear to you. See, the first cluster got what? 1 3 4 6. The second cluster got what? The second cluster got what? 2 5 7 8. If you can see it, this figure. Okay, and then after clustering, we located their class with our original database. So we found that 1 was having 0 class, 3 was having 0 class, 4 were having 0, but 6 was having 1 class. So we assume that this 6-1 is a faulty sample and I will eliminate it. Here also, this is just an illustration for the concept. Here 50 is the faulty sample, so I will eliminate it. And because most of the samples are one here, belong to one class, this is malignant cluster. And here most of the sample are belong to 0 class, so it is benign cluster. So doubtful samples are identified and they are eliminated. Okay, and then remaining samples are taken for training. And then BPNN was trained, backpropagation artificial neural network was trained, and classification was done. Okay, so this was one paper related to breast cancer ultrasound breast cancer classification. We did some other work also, so I think we have limited time, so I'll not discuss all, but let us discuss one more. There was one paper on multi-criteria feature selection also. Okay, so that already I have explained you in PPT. This was one paper in which we integrated one radiologist also in the whole pipeline. It means that, let us see the block diagram. This one. See, the left. So whether my cursor is visible to all of you or not?
Yes, sir, it is visible.
Okay. So this is a training data. This is the training data, grayscale training data. Okay. Noise removal. The second step is noise removal. The third step is feature extraction. Fourth step is normalization. Then feature selection. Then training of BPANN. This is training of BPANN. Okay. Then we have testing phase. Online system means testing. Again, testing images, speaker noise removal, feature extraction, normalization, and then classification using BPANN, neural network. If the classification of neural network, the classification result of neural network is matched with the radiologist evaluation, what radiologist is classifying manually. If their results match, we consider it final. If they do not match, again we take another classifier SVM. And then the result of SVM is also is considered final. So it is a kind of majority voting only. Majority voting between artificial neural network, support vector machine, and the radiologist. Okay, so all the three are combined for taking the final decision. Okay, so I hope this is clear to you. So I think I'll end the session here. Continuously, I think it's approximately 1 hour 40 minutes. So the questions are welcome from you all. I'll be happy to answer some questions. Any doubts to any one of you, you can write in chat box also. Or you discuss any of your own problems, or if you want any kind of suggestion for your own problem, we can discuss now. We have some time. Any questions from the participants? Okay, someone has wrote multi-dimensional hyperplane. So what is the question, Deepak? Is Deepak here? For this non-linear, we use SVM parameter. Deepak has asked some questions, but I think whether he is there or not, he has written something. We put multi-dimension hyperplane.
Sir, here it is. Deepak has written that no, sir, it was not a question.
Okay, he has given some answer which I was asking, maybe, or some
Yes.
suggestion might be he might be giving. When we go for classification, every time it gives different accuracy for same data. Yes, because this is a question from Nivedita Singh. So that is because see what happens whenever you divide the data for training and testing. Okay, so the data division always takes place randomly. It always takes place randomly. Either you'd use 10-fold, or you use 5-fold, or you use holdout. Okay, So when the data is divided into training and testing, when the data is divided into training and testing, the data division always takes place randomly. So because it takes place randomly, obviously the performance will be different because your whole data is same, but but during the data division, the samples that the model is taking is very random. The data division is taken randomly. In a class of say 100 students, I go daily and suppose I select 10 students randomly, so they will be different. Okay, so that's why the accuracy is different. Okay, so sir, which algorithm are you applying for language disorder? So for see, language disorder means we are trying to analyze language disorders using two modalities, EEG and speech. We are using two types of signals. One is EEG and other is speech. Okay, so the machine learning techniques will be same. Whatever we are discussing in this class, deep learning, machine learning, the techniques remain same, but you have to customize it according to your the characteristics of your data. Uh, we record EEG data and speech data simultaneously while interviewing the subject. We are giving some task to the subject, or we are asking some questions to the subject, and during that time we are recording it, his or her EEG data as well as speech data, and then we are doing some quantitative analysis like feature extraction, selection, and then we are using some new deep learning techniques and advanced techniques for classification. Okay, so as far as algorithms are concerned, there is not much change in algorithm, but the point is that what is your study protocol, that is important, how you are recording the data, what kind of task you are giving to the subject. So finalizing these things are very important, and that's why collaboration with clinicians is very important in these cases. I hope it is clear. Can you suggest a good research topic in data mining? So many good topics are there. So in this presentation only, I have told you so many topics. Okay, you can work on multi-model imaging of all diseases, not only breast cancer, many diseases. Most of the existing studies are using single modality. So we can go for multimodality analysis. Okay, and lot of studies are there in biomedical signal processing also, detecting different mental disorders, language disorders, studies on children who are specially abled. Lot of topics are there. You can see some recent journals for that. Some good reputed journals like IEEE Transactions and Springer Elsevier. You can search for some good papers, and accordingly you can decide. Is it okay? The answer to your question is very broad. So many topics are there. Is it okay? Masula Vinoda. How to stabilize the results in that case? In that case means you want to say classification accuracy, Stella A. In that case means you are talking about different classification accuracy, right?
Yes, sir.
Okay. So actually, so there are some methods to stabilize the result. We can use some parameter tuning methods like Bayesian optimization, grid search. So these are some techniques which you can look into, but the results are not exactly same always. They will slightly differ if they're changing very much. Like for round one you got 80, in round two you are getting 30. So it means that there is problem in your data or there is problem in your algorithm. There is not so much change. It will be 80, 82, 81, 79. The change will be like this. Okay, so there will always be some change because of the random behavior of these algorithms, but the change will not be much. For stabilization, you can run your experiment multiple times and average the results. By that way, you can report in your research articles. Otherwise, you can use some optimization techniques also. Like I told you, Bayesian optimization, and so many optimization techniques are used that can be used. Am I able to answer?
Yes, sir.
Okay. So finally, okay, so is it possible to have one hands-on session by you on breast tumor segmentation classification? We will try for classification. Okay, maybe for segmentation also. Let us see. We'll have to prepare accordingly. So maybe on the last day, because all the lectures are pre-planned. there was one lecture of mine on last day, but that will now be taken by Dr. Mridu because today was her scheduled lecture, and because she has got some emergency show, so I have to take it. So if I get one more lecture, if some lecture is cancelled due to some reason, then I'll definitely demonstrate. Okay.
Okay. Any other question from participants?
Okay, sir.
Okay.
Okay. So thank you, sir, for such a knowledgeable session. Thank you, Bikesh sir. And participants, you can leave now, and tomorrow the first session will start at 10:30. Thank you.